Good day and welcome back to the fourth part of our discussion on Green's theorem. Now if you are following along with the note sheets, which I recommend you all do, you'll note I've jumped to page 5. Typically when we're going over Green's theorem in class face-to-face, the second day of discussion would start off with the material on page 4 of the note packet, which is really a review of what we've encountered in this most recent chapter. That would be line integrals with respect to arc length, with respect to x, with respect to y, line integrals over vector fields, the fundamental theorem of line integrals, and Green's theorem. Kind of what are the statements, and more specifically, when and how do we apply Green's theorem and the fundamental theorem of line integrals. I would strongly encourage you to take a look at page 4 of the completed note packet and to really think about these key ideas. In today's video, what we'll do is continue our exploration of these topics by investigating two very common examples. So, to begin, in our first example, we're asked to evaluate the line integral, where C is the circle, x squared plus y squared equals 4, oriented in the counterclockwise direction. So that is to say our curve of interest is a circle centered at the origin with radius 2, and it has a counterclockwise orientation. So this looks as though it would be an ideal scenario for us to apply Green's theorem. And remember, when we apply Green's theorem, the line integral p dx plus q dy is converted into a double integral. But it's not the order of the terms that determine the p and the q, it's which differentials they are paired up with. So we do have to be careful. In this case, we would have p dx q dy. And I joke a little bit when I say this, but remember your alphabet, x, y, p, q. So just restating this so it's in the order we are more familiar with, we would have the line integral of 2y plus the square root of 1 plus x to the 5th dx plus the quantity 5x minus e to the y squared dy. And if we wanted to think about this from the perspective of a line integral, this would be extremely difficult, and based upon a few of these parts here, I would maybe even say impossible for us to evaluate directly. So instead what we'll do is apply Green's theorem as we have the ideal scenario. This becomes the double integral over the region D, which is this nice circular symmetric region bounded by our curve. And our integrand is dq dx minus dp dy. So that would be the partial with respect to x of q minus the partial with respect to y of p. And note, I am perfectly okay if you skip writing out which partials we are calculating, and in this case if you jumped directly to 5 minus 2, but I will typically do that just to make sure we see exactly where each of these quantities come from. So note q sub x minus p sub y. That gives us the double integral over d of 5 minus 2. So if we pull the 3 out, we have the double integral over the region D of 1. And the double integral over a region of the function 1 really is calculating for us the area of that enclosed region D. So I could instead write this as 3 times the area of D. And as D is a circle centered at the origin with radius 2, it has radius 4 pi, and we end up with 12 pi. And the takeaway is, as long as we recognize that we can apply Green's theorem, and we do so correctly, this turns out to be an extremely reasonable problem. For the second example, we're asked to do something very similar. We're given a line integral, and we are asked to evaluate it over the top half of the circle oriented in the clockwise direction. So let's go ahead and sketch this out. So the circle that we are starting with has a center of 1/2, 0, and it has a radius determined by the square root of 1/4. So remember, 1/4 on the right is 1/2 squared, which tells us we have a radius of 1/2. So we're centered at 1/2, 0, and it's a top half of a circle of radius 1/2. So it would go through the origin, and it would go through 1, 0. And we are oriented in the clockwise direction. So I would like you to pause the video for a moment and just kind of write down or make a mental note to yourself, which of our recent properties should we attempt to apply? And note, Green's theorem does not apply to this example. We do not have a closed curve. It does not start and finish at the same point. But instead, maybe we can use a fundamental theorem of line integrals, or if not, we'll just be stuck coming up with a parametric description. So we have this kind of mental thought process we can go through. So let me make a few kind of observations. We have the line integral over the curve C of y squared over 1 plus x squared dx plus 2y arctangent of x dy. And note, a line integral of this form is a line integral over a vector field. And in this case, that vector field f has a first component, y squared over 1 plus x squared, and a second component, 2y arctangent of x. And before coming up with a parametric description and going back to our 16.2 methods, part of our thought process should now be to ask, is this vector field conservative? And how we can check and see if the vector field is conservative is calculate a few partials. So we want to think p sub y and q sub x, where remember, p is the entry in the x component, q is the y component of the vector field. So p sub y would be the partial with respect to y of y squared over 1 plus x squared, which is 2y over 1 plus x squared. Q sub x is the partial with respect to x of 2y arctangent x, and we see things are working out nicely. 2y over 1 plus x squared. So we do have a conservative vector field. And because it's a line integral over a conservative vector field, that means we can evaluate it using the fundamental theorem of line integrals. And what the fundamental theorem of line integrals tells us is we will get back little f of the finish point of the curve minus little f of the starting point of the curve. Where recall, little f is the potential function for this vector field. That is to say, the vector field big F is really the gradient of some function little f, which makes the first component f sub x and the second component f sub y. So what we need to do in order to evaluate is we need to find f sub xy with the partial with respect to x of f is y squared over 1 plus x squared, and the partial with respect to y of little f is 2y arctangent of x. And I want to note here that based almost purely on inspection, we can think with respect to x, y squared is a constant, and the antiderivative of 1 over 1 plus x squared is arctangent of x. So if we undo the partial with respect to x, we would get back y squared arctangent plus a constant possibly involving quantities with y. Similarly, if you undo the partial with respect to y, the antiderivative of 2y is y squared. Arctangent is a constant with respect to y. And in this case, our constant with respect to y, our constant with respect to x, we can just make 0. And we have f of xy, the potential function, y squared arctangent of x. And the problem now is essentially completed. It's a function evaluation. F of 1 comma 0 is 0 squared arctangent of 1, minus f of 0, 0, which is 0 squared arctangent of 0. And note, 0 times anything is 0, so we end up with 0 in this case. And let me make just a couple observations. If I change the problem ever so slightly here, just for fun, if I was instead to pick my curve to simply be a line segment going along the x-axis joining 0, 0 to 1, 0, and we called this curve C2. The question that we could ask, for this vector field f, what is the line integral over the curve C2? And hopefully you were all shouting at your computer screen, 0. The reason being, we have a conservative vector field, which means it's independent of path. As long as we start at the origin and finish at this point 1 comma 0, the path itself is irrelevant. It could do kind of any crazy thing that we want, and you will still get back precisely that same value of 0. Another observation I want to make is we do have to be very careful about what property we apply. Sometimes both the fundamental theorem of line integrals and Green's theorem apply, but more often than not, that is not the case. So really make sure you have the hypotheses satisfied and you apply the properties correctly. At this point, if we were meeting face-to-face on campus, we would be midway through our second day of class on Green's theorem, and I would be passing out to you a worksheet to complete, kind of fun with line integrals. In fact, if you turn to page 6 in your note handout, you can find that exact worksheet. And I recommend giving yourself 20 to 30 minutes before viewing the next video where we will discuss several of the problems. You can also find full solutions posted on Canvas as well. So stay tuned and take care.